We are doing 10.2, Properties of Power Series. This is a really important section. There are properties that have implications that go very deep. You need to really understand what these are saying and then practice applying them. We're going to do 1,000,000 FRQs to practice these properties. This is kind of our last section, sorta. We do have another section that's going to look specifically at a Taylor series. This in general is a power series, but a Taylor series is a type of power series. So everything we learn about a Taylor series will apply to what we're learning this chapter. Or in other words, whatever we learn about the properties of power series will apply to a Taylor series. All right, so let's just go through this. So earlier in a video, we learned what a power series is, and this is the form. And the center's at A, and so you can see that the center, you will know by looking at this series whether you have a center at 0 or some other point. As I said earlier, the Taylor series is a type of power series, and also from chapter 9, we had a geometric series, and we learned the sum of an infinite geometric series of this form, where the first term is 1 over 1 minus r. It's the first term divided by 1 minus r, but there was a condition. The absolute value of r had to be less than 1. Okay? Now, r was just your common ratio, but we can replace that with x. So if we replace all the r's with x, we get the same series, but the sum is just 1 over 1 minus x instead of 1 over 1 minus r, and the absolute value of x must be less than 1. We do that just to make it look what you're used to having as x is your variable. So we call this f of x, our function, is 1 over 1 minus x, which equals to this power series. So I guess I probably should have written it differently, but basically f of x equals that, where f of x is 1 minus x. So last chapter we learned the sum of an infinite series, so now we define the sum this way and equals this series. So just a different way of looking at it. Now, you need to know some vocabulary. So because this only worked when absolute value of x is less than 1, you have to realize that this converted looks like that. It goes from -1 to 1, between -1 and 1. So this is called the interval of convergence. The interval of convergence are the values of x where the series represents the function. And we realize when x is bigger than or equal to 1, this no longer is valid. So we need to find out what values of x will actually work for the series called the interval of convergence. Very common question on AP test. Now the radius is just half the interval. So if you look at this one here, we went from -1 to 1. The radius, like if you think of a circle, if that's the whole interval, the radius is half, right? That distance, half that distance. That's the idea of radius of convergence, r. So if the distance is 2, because from -1 to 1 is 2, therefore the radius will be 1. Or another way to look at it, the center's at 0. The distance from the center to the outer edge is 1. So that's how we get our radius. It just tells us the distance from the center to the end. So that's some vocabulary. Now, let's do some examples. And how are we going to do this? You need to know chapter 9, all the tests we did in chapter 9. But the good news, we mostly stick with ratio test but not always. So let's do part A. How do you find the radius of convergence? Well, we had convergence tests in chapter 9. And we learned when you had exponents and factorials, ratio test was bueno, mucho bueno. So we found R, and we're doing absolute convergence. So we're going to do absolute value. We're going to do a sub k plus 1, which is x to the k plus 1 over k plus 1 factorial, divided by a sub k, which is just x sub k over k factorial, and we did the limit as k goes to infinity. Well, we're going to multiply by the reciprocal, so we're going to get x to the k plus 1 over k plus 1 factorial times the reciprocal of the denominator, and we are going to simplify this. We have one extra x on top, so those will cancel out, leaving an x there. Let me make my pen fatter. Then the factorials, this is all the numbers from 1 to k multiplied. Well, this is 1 to k, but they also have a k plus 1 extra. So x is a constant. Why is x a constant? I will explain that to you. This represents a function f of x. So if you want f of 1, x will be a constant 1. If you want f of 5, x will always be 5. So x is just a set value where you're evaluating this function. So that is your constant. K is changing. So the rules of limits, you can pull a constant out in front and then take the limit as k goes to infinity of what's left. Do we just have 1 over k plus 1? Let me double check in my brain. Yeah, which is 0. Well, I'll take that back, which is x times 0. So that's x, that stays. This limit is 0. So we have times 0. But any constant times 0 is 0. So what did the ratio test tell us? If r, absolute value r, is less than 1, then the series converges. If it equals 1, it's inconclusive. If it's bigger than 1, it diverges. But we're doing absolute, so yeah. Or we can do this. I could write a different way for you. This is the way we normally saw it. 0. So anything from 0 to 1, not including 1. 1 was inconclusive, bigger than 1, divergent. But since this equals 0, this always converges. So the interval of convergence, I will do that, is from negative infinity to infinity. It doesn't matter what your x is because it's times 0. Your radius r is going to be infinity because from the center 0 to infinity is infinity. So that's your radius of convergence, and that's example A. Let's do B. Now, look, power of k, power of k, power of k. What is the obvious test to use? Is it not the root test? Is it not? We will do the root test. So p, or rho, is the limit as k goes to infinity of the kth root, and we're doing absolute convergence, negative 1 to the k, x minus 2 to the k, over 4 to the k. Well, this is pretty easy. The root and all those powers cancel, so we're left with this. The limit as k goes to infinity of absolute value, the negative 1, absolute value gets rid of that. So it's x minus 2 over 4. Now, remember x is a constant, so this is just x minus 2 over 4. There is no k here, so it doesn't matter if k goes to infinity. There is no k to worry about. Now, this is the same as the ratio test. This has to be less than 1 to converge, right? So we multiply both sides by 4, and we get a 4 there. Now, converting this to, I don't know what I'm saying. You can convert this to be this. I don't know how to say it. Negative 4, x minus 2, 4. If you want to get rid of the absolute value, that's how you write it, like that. You add 2 to everything, and you get an interval of convergence. So that is just the same as that without the absolute value. Now, your function converges. So converges when? I'm going to write it this way. Converges when any of this is true. And we can erase this. Now, that's not my interval of convergence. Why? What happens when this equals 1? It's inconclusive, right? When this equals 1, it is inconclusive. I'm running out of room, so I'm going to overlap part C, which it's okay. Let me move this over so I have more room to work. So here's what I'm saying. If this were to equal 1, it might converge, it might not converge. So I have to consider those cases of what happens. So at negative 2 and 6, it equals 1. So I need to let x equal negative 2. And I'm going to put a negative 2 there and see what happens. So we will get this negative 1 to the k. I'm going to put a negative 2. Negative 2 minus 2, that's going to be negative 4 to the k, all over 4 to the k. That can be rewritten. I'm going to put everything, there's no equals there, lame-o, equals. Since they're all to the k power, I put them all together. And I'm going to get 4 over 4 to the k, which is 1 to the k, which is geometric. This is a divergent geometric. So when x is negative 2, it results in a divergent. Then I'm going to plug in 6, because that's the other time when p equals 1. So I'm going to put 6 right here. That's going to get me a 4. So I'm going to get negative 1 to the k, 4 to the k, over 4 to the k. And you will notice these cancel. So you get negative 1 to the k. Now, if you add those forever, think about it. You're going to get 1 minus 1 plus 1 minus 1, on and on and on. Is that going to approach a single number? It's not. It's going to bounce back and forth between a couple numbers. Therefore, in this case, that's divergent also. So both at negative 2 and negative 6, it's divergent. So this is divergent. So both at negative 2 and 6, it diverges. So now we have our interval of convergence is going to be negative 2 to 6. Now, on the previous one, we couldn't state this as the interval because we didn't know what was happening at the endpoints, at negative 2 and at 6. Now that we found out it diverges at both, we're going to have not equals on both, and we can state that as the interval of convergence. I have one more to do, and I'm going to erase all of this to get room. I didn't give myself enough room when I made my note sheet. Let me delete this. Ooh, I had it. Okay, try it again. Delete. Okay. Letter C. I have factorials and I have exponents. I am going to use ratio test for C. And we calculate our R as the limit as k goes to infinity of a sub k plus 1. So on top, we're going to do our k plus 1 divided by a sub k, which is the original function. And let's do some simplifying. There's one extra x on top. That's going to leave an x. And all the numbers up to k will cancel all numbers up to k, leaving a k plus 1 on top. So this equals the limit as k goes to infinity. Now, x is a constant, so I could pull the x out in front, absolute value of k plus 1. And that's going to go to infinity. X times infinity is going to be infinity. All right? Now, obviously, if x is 0, it's a different situation, but it's going to be infinity for all values of x not equal to 0. So in order for a function or a series to converge, in the ratio test, R must be between 0 and 1, including 0. This clearly is not. Okay? So this always diverges except at x equals 0. So, yeah, our radius of convergence would be 0 because it just is. I don't know what else to say. What's the radius of or what is the interval of convergence? I'm going to say it converges if x equals 0. At that one point, because if this is 0, 0 times any number is going to be 0. So that is that example. Let's keep going. Next theorem. Convergence of a power series. So this is the general form of a power series. Centered at A, that looks kind of weird. Centered at A, not centered at A converges. Centered at A converges in one of three ways. So the first situation that could happen, the series converges everywhere from negative infinity to infinity, and the radius will be infinity. Okay? Or it's possible it converges when x minus a is less than r, and diverges when x minus a is greater than r. We saw the example, and the radius is r. That was our second example, I believe, or first. Maybe the first two. I erased one. Oh, that would have been B. In example B, which is erased, we had a convergence when this was less than some number, and we solved for that. And the last one, a series converges only at one point, the center, and therefore the radius of convergence is just 0. So more examples. Use the ratio test to find the radius and interval of convergence for this function. So we know R is the limit as k goes to infinity. Absolute value, we need a sub k plus 1. So that's going to be x minus 2 to the k plus 1 over radical k plus 1 all over the original function Now we're going to multiply by the reciprocal, so we're going to rewrite this. And then we reciprocal this. And then the top has one extra one of these. So we're going to be left with the x minus 2. And don't forget our absolute value. Since x minus 2 is a constant, we pull that in front. And then we're going to have this. Now, if you take that limit, you're going to get 1 for that limit. We could combine those into, yeah, I'll do that for you. We can combine both of these into one square root. You might be able to see it better. So that's just going to be 1. So that's going to be x minus 2, and that's our r. And when does this converge? When the absolute value of r is less than 1, which we can rewrite as -1, x minus 2, +1. Add 2 to all three, we get 1 to 3. All right? So this here will be a region where it converges. Now, it's not our interval of convergence because we don't know what's happening at 1 and 3. We need to test those 2 points to come up with our interval of convergence. We just know it converges according to the ratio test. It converges here. But when this equals 1, which occurs at 1 and 3, we're not sure. So we're going to test those. Let x equal 1. If we put a 1 here, we get -1 to the k over radical k. And we know that converges. This is an alternating series whose terms do what? Decrease in magnitude to 0. Therefore, convergent at 1. Let's try our other endpoint. Let x equal 3. When we plug in a 3, it'll be 3 minus 1. So we're going to get this 1 to the k over radical k, which is just 1k to the 1/2. This is a divergent p-series. So it diverges at 3. Therefore, our conclusion, our interval of convergence, at 1, it converges, but at 3, it diverges. So that's our interval of convergence. If it asks for a radius, I don't know if it does or not. Let me see. No, we just want the radius and interval. So the radius, well, this whole distance is 2. So the radius would be half that, which would be 1. That's that part. All right, now combining power series. This is the section. These 3 and the following 2 are really important. You will use these over and over and over. So make sure you are understanding the concepts here. So we're given 2 power series. One with a coefficient c of k and one with a coefficient d of k. And they, I don't know what that word's supposed to be. It's not supposed to be converse. But f of x associated with the c of k and g of x is d of k. So, converge. Now I know what it's supposed to say. Converge, meaning, this is what it means. This equals f of x, and this equals g of x on some interval I. Just like the geometric series converges when x, absolute value of x, is less than 1 that we looked at earlier, there is some interval where f of x is this infinite series and g of x is this infinite series. So I think this summarizes it. F of x is represented by this power series, and g of x is represented by this power series, both on the interval I. So I is just from some x to some x. So I could be something like this, from A to B, just some interval. Could be closed, could be open and closed, but some interval. You have a power series that represents two functions. So here's what the first one says. If you want to know what the power series is for the function f plus the function g, or subtracting, you can combine each series together. So the sum of each individual function, to get their power series, you add or subtract their actual series together. So that's what that's saying. That one's pretty straightforward, should make sense. Here's where it gets trickier. So I will actually, how can I explain this? Suppose m is an integer such that k plus m is greater than or equal to 0. So that must be a condition, and usually it's not an issue. It always is when we work with these. Now, what is this saying? If I multiply this series by x to some power, I can move that x inside, and so we can just do x to that power plus, you just add exponents basically. You're adding m and the k. So you can distribute this inside of the series. But what does it have to do with anything? Here's what we're saying. If you have a function, we'll look at the function here. You have a function and you have its power series that converges on the interval I. So what happens if you multiply your function, your f of x, by x to some power? Well, you just multiply your series by x to that power. In other words, the x comes on the inside. This is very powerful. You're going to see some examples of this. But just realize you can multiply your function and your series by x to a power. And the new series will also still converge on I. So if the original converged on I and you multiply by x to power, it still converges on I. And back to number 1, when you add two series together, if each original converged on the interval I, the new series, when you add or subtract them, will converge on the interval I. And then the third one, this one's probably more useful. It's a composition of functions. So you have a function h that's some constant times x to a power. Now, watch what's happening. We're taking this x here and replacing it with bx to the m. It's a composition. We're placing h in for x. Okay? So in other words, we're taking the h function, which is a constant x to the m, and putting it inside of the f function. And that series, what will the series look like? Well, you can replace the x in the series. And so I didn't rewrite this for you, but f of h of x, so if you do a composition of functions by replacing x with a constant times x to the m, that's going to equal your original series here, but with x replaced with h of x. So that's what this is saying. You replace x with h of x. So you replace this x with your composition function. Now, suppose your old interval I was from A to B. what this is saying, h of x is in I. So now you are going to put h of x here. And you have to solve for x to get your new interval of convergence. So that's what it's saying there. These are used a lot. You need to kind of get a good feel. I know I kind of explained this, but you need to, as we do the example problems, you need to see how they're being applied and understand it completely. I know you can kind of glance over and say, oh, I get it, but pay close attention. So let's look at this. We know this is a geometric series, the sum of a geometric series, as long as absolute value of x is less than 1. And so if we want to get the power series for this, we know it's this, which is the geometric series with the a sub 1 of 1. The first term is 1. How do we get x to the fifth over 1 minus x? What will the power series for that look like? Well, let's look at these rules 1, 2, and 3. What are we trying to accomplish? We want to multiply by x to a power. Take our original function and multiply by x to a power. So let me take my original function, 1 over 1 minus x equals 1 plus x squared plus x cubed plus dot 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 plus x to the k plus dot dot dot. Now if you want that, you have to multiply this by x to the fifth. But you know what? I probably should write the series for this also. So let me back up here a step. Because you need to be okay with the summation notation form and the expanded form. So let me move this over and do this. So I'm allowed to multiply by x to the fifth, which in turn multiplies this by x to the fifth, if you can see that. So now I have a new function, x to the fifth over 1 minus x. And what does the rule say? If you look at this, you're allowed to take that x to the m and move it inside and get that new power. So what does that do for us here? This will be x to the k plus 5. And on the series, it'll be x to the fifth plus x to the sixth plus x to the seventh dot 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 plus x to the k plus 5 plus dot dot dot. So hopefully that makes sense to you. That will be that series. So we found the series starting with the geometric and ending up with the new series of x to the fifth over 1 minus x. So make sure you notice that both sides are being multiplied by x to the fifth. So not only do you have a new series, you have a new original function. So you've created a brand new power series for an unknown, basically an unknown, you created an unknown series for a new function. Basically, that's what we've done. Okay? So that is our first one. Let's look at the second one here. We know this, and you want this. What's different? You'll notice the x changed to a 2x. How do you do that? Okay, so what happened, this x has been replaced with the 2x. That's going to be composition. You replace the original x with the new function h of x, where h of x is a constant times x to a power. So what's the h of x here? If we do h of x is 2x, and we replace this for x, we've done it. Okay, if that makes sense. So let's start with this 1 over 1 minus x. We'll call that our f of x. So let me back up a little bit here. So f of x is 1 over 1 minus x. And then the series for that is x to the k, which is 1 plus x squared plus x cubed plus dot 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 plus x to the k plus dot dot dot. Now make sure you're comfortable with summation notation, why you get this series from this. But here's what we're going to do next. We want a 2k there, or 2x there. So that is f of h of x. You replace all the x's with 2x. So then, in our summation notation, that x is replaced with a 2x. And in this, you replace all the x's with 2x. Now what you need to know, we're assuming the original had this interval of convergence, right? Which is the same as that, but my new interval of convergence is going to change because I'm replacing x with 2x. Divide everything by 2, so now that changes to a new interval of convergence. So these two first ones, the interval of convergence don't change on these, but this one it does, and you need to place h of x inside your interval and solve for your new x. And that's what we did on example B. For the third one, I will write it out again. This will be 1 over 1 minus x. So this is your function, calling it f of x. Now what is the series? It is x to the k, which is 1 plus x squared plus dot 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 plus x to the k plus dot dot dot. Now the question is, how do we get this from that? So what has happened? So x has been replaced by a new function minus x squared. So again, we still have a composition. So this will be f of h of x is 1 over 1 plus x squared. Because if you place this in for x, it becomes that. That was what we wanted. So now you just replace all the x's with minus x squared. And we have this. 1 plus minus x squared plus minus x squared squared plus minus x squared to the k plus dot dot dot. So that's what's going on, but we're going to have a new interval of convergence because we're going to have this. Okay, what happens if you multiply everything by -1? Your inequalities flip. And then if we square root both sides, you're going to get, or all three of them. Oh, that ain't going to happen. Okay, let me back up here a little bit. So let's think about this. And this will make sense to you, hopefully. Let me get my eraser, no, the highlighter. This is always positive, right? So it's always going to be bigger than -1. So in essence, here's the thought pattern. I can replace this with a 0 because I'll do this for you. Let me erase this. Could I not do this? That's a -1. Isn't that true? So 0 is bigger than -1. And since this can never be negative, I don't have to worry about that. That's my edge case. So now think about this. What values of x can I put here? If you think logically through it, I could put negative values and positive. So you end up with this. You end up with what you started with. So kind of logic through that, and hopefully that makes sense to you. Okay? All right, let's keep going. Here is the other. So there's 5 things you can do to a function and its series. So we have a function and its series, a function and its series. So the first thing, you can add the functions up and add the series up. The second thing, you can multiply your function by a power of x, and then you multiply your series by a power of x. And then the third thing, you can replace your function x with the h of x and do a composition if you do that also for the x in the series. So composition, multiplication by power of x, and adding or subtracting 2 series. Those are 3 of the 5 things you can do to a series. These next 2 are very powerful. So you have a series, f of x, and it equals this power series. If f is differentiable, which implies it's continuous for all values where x minus a is less than r, so in the radius of convergence, then how do you find the derivative of your function? I want the power series for the derivative of that function. Very simply, this is what you do. The derivative of this is the derivative of every single term here. Now here's where your brain is going to trip out a little bit. K is your variable. That's what's changing. X is a constant because you want the derivative at some point, maybe 5, then x will be 5. If you want the derivative at 1, your x will be 1. So your x you have to treat as a constant. So what's the derivative of ck, which is a constant, times x minus a to k, which is a constant in this case? Well, it's the power rule. The k comes out in front and you subtract 1 from the exponent. Well, the k came out in front and you subtract 1 from the exponent. And you're going to have that same radius of convergence. Okay? Then the same thing by integrating. If you want the Taylor series or power series for the integral of f of x, well, you can integrate this. And how do you integrate that? You add 1 to the exponent and you divide by that, right? So you add 1 to the exponent, you divide by that. And don't forget the plus c. And it converges on that same radius or interval of convergence. Okay, here we go. Here's our next example. So f of x equals 1 over 1 minus x. What does the power series look like for the derivative of f of x? Well, f prime of x, if we rewrite this, this will be 1 minus x to the negative 1. So this is chain rule. It's box to the negative 1. So it's negative 1 box, subtract 1 from the power, times the derivative box, which is negative 1. So this will be 1 over 1 minus x squared. So that is the derivative of x. But how do we find that? Well, we can just integrate that. So it will be add 1 to the exponent and divide by that. Or if you want to do the series, you integrate each term in the series to x squared over 2. That first one will be x plus x cubed over 3 plus dot 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 plus x to the n plus 1 over n plus 1 plus dot dot dot. And there's going to be a plus c. I'll put the c in front. Okay, so now for this series, or for this function, you have the power series for that function. And I forgot the plus c here. So that may not seem like that big of a deal, but it's pretty powerful what's going to come out of that. Okay, you're going to get some cool things from that, believe it or not. Let me think. Are we good so far? I think we are good. think they re-indexed it, but we're okay. Oh, let me back up a little bit. I actually integrated it instead of taking the derivative. Wow. That was so bad. I'm getting ahead of myself. I apologize. Sorry if I wasted your time. I got to take the derivative. Okay. What's the derivative of that? You bring the k in front and you decrease the power by 1. Okay, I know what we need to talk about here, though. We do need to talk about the derivative of 1 is 0, and you get 1 plus 2x plus 3x squared plus dot 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 plus nx to the n minus 1 plus dot dot dot. So here is the problem. Okay, now this one had this interval, so still the same interval. But let's look at our series here. If you plug in 0, do you get the first term? And the answer is going to be no. Because you get a negative 1 power. You want a 0. So we can re-index this a couple ways. We can start at 1 instead, or we can add 1 to both of these to get, so either way. So instead, we could start at 0, or start at 1 instead, or we can rewrite this. And so this is something that happens when you take derivatives and integrals. Things get messed up sometimes. So we're going to still start at 0, but what we're going to do is increase all our k's by 1 to make it match. Now this will get us the proper answer. Or like I said, start at 1. But you usually want to start at the same thing you started by. So it's called re-indexing. All right, and that also is going to affect our term down the line. So this one, and those are k's, not n's. I apologize again. I am messing up here. But our re-indexing can re-index this one also to k plus 1 and k. So let me erase this. So if we leave it starting at 1, then we're okay. We're still going to get that as our general term. But if we re-index it and change all of our k's to k plus 1, we're going to get this. Okay? So we're just changing our index. It just makes it work starting at 0. My advice to you is to start plugging in numbers, starting with 1 here and see if you get that. And then start plugging in numbers starting at 0 and see if you get that. And it should work out properly for you, and you'll get a better understanding of the indexing of that. Okay? Wow. That was a lot of, I don't know, hoopla. All right, let's look at this next example. We're going to integrate. I like this. So we're going to integrate f of x dx, which will be the integral of 1 over 1 minus x dx, which will be, so if you integrate this, you add 1 to the k. That's where I got ahead of myself last time. Divide by k plus 1. And you integrate all these. The integral of that is x squared over 2, x cubed over 3, dot, 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 plus x to the k. Oh, that's supposed to be a k. That's why I'm messing up. Those are supposed to be k's. No, it's an n. Wow. No, it's k. It's k. It's k. Wow, sorry guys. My brain's not working well today. So we're integrating, so it's x to the k plus 1 over k plus 1 plus dot dot dot. Now double check this. You put in 0 here, you get 1, and you get 1, and it works. You put in 1 here, you get 2 and 2, so that works. So our numbers are fine for this one. But what's the integral of this? That's a u sub. U is 1 minus x. Du is minus 1 dx. Do we have a minus 1 dx? Now we do. So this is negative du over u, which is negative ln u, which is absolute u, which is negative ln absolute 1 minus x equals, and we have this series. So let me write this out. We have x plus x squared over 2. Oh, I didn't get my original. I am so bad right now. X to the k plus 1 over k plus 1, which is x plus x squared over 2 plus x cubed over 3 plus dot 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 plus x to the k plus 1 over k plus 1 plus dot dot dot. Now the last step that's going to happen is we multiply both sides by negative. So now we have this ln of 1 minus x. So now we have actually found a new power series for ln's. And we found that without plugging in term by term, creating the, sorry, that's the wrong one. Creating a power series, you have that formula. Instead of using that formula that we did all our power series in the first section, we can actually create power series by integrating, taking derivatives, and doing other weird things likewise. And so there's a lot of things going on here. But now we have found this, and it's going to be just a negative x to the k plus 1 over k plus 1, which is, just make these negative and we're good. Minus, I don't know why I keep putting plus, x to the k plus 1 over k plus 1 minus dot dot dot. All right, that is our series. Let's just keep going here. Okay. This is pretty cool. You could, and this would be a pain, create this by doing this. The centers is 0. Well, f is 0, sorry. Plus f prime is 0, x plus f double prime of 0, x squared over 2 factorial. And you could do that on and figure it out. But let's use the 5 things you just learned to figure this out. Now, a little tidbit that you need to know, the integral of 1 over 1 plus x squared dx is arctan. Do you remember that? Plus c. Do you remember that? That is something you should know. So I say to myself, wow, if I can integrate that, but I don't know that, but I know this. I know this, which is 1 plus x squared plus x cubed plus dot 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 plus x to the k plus dot dot dot, right? That's the geometric. But then I wish upon a star that had a plus x squared. That's when I do this. If we call this f of x, I say h of x is minus x squared, and we did this in an earlier problem, f of h of x equals 1 over 1 plus x squared equals, I'm just copy and paste it because I don't want to do this over again. Where is it? It is right. I know I did it. Did I not? Okay, maybe I'm on drugs and I don't realize it. I thought I did. Oh, here it is. I did. It's right here. It's right here. This is the series that we're looking for. So I'm going to copy and paste it because we already did this. Right down here. Nice. I'm going to erase this. And I'm going to move this up higher. So that's really cool. So we did a composition where we found f of h of x to get that. Now if I were to integrate both sides, this would become arctan. Pretty sweet. And we will get this, arctan of x equals, and then we have to do some work here. This will be negative x. Okay, let me split this up. This might be a little bit of craziness here. I am going to rewrite this as negative 1 times x squared all to the k. Okay, and then I will integrate this. Yeah, we'll integrate. No, I'll rewrite this. 1 minus x squared plus x to the 4th plus dot 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 plus, okay, I'm going to have to do something weird here. I'm also going to split this to negative 1 times x squared all to the k plus dot dot dot. Where is this getting me? Hopefully your brains aren't too fried. I forgot my dk. And this integral dk. It's negative 1 to the k, x squared to the k, which is x to the 2k, dk, 1 minus x squared plus x to the 4th over, no, wow, this is pretty bad, guys, sorry. That's negative 1 to the k, x to the 2k plus dot 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 dk. All this to say arctan is, now how do we integrate this? That's not going to change because it's just negative 1 to the k power. Okay, then I add 1 to that exponent and divide by that. So I'm going to get x to the 2k plus 1. And I'm going to divide by 2k plus 1. All right, so that is my summation notation of that, which is x minus x cubed over 3 plus x to the 5th over 5 plus dot 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 plus negative 1 to the k x to the 2k plus 1 over 2k plus 1 plus dot dot dot. And there's a plus c on both of these. Whew, that's crazy. So I think we're done with this. That is crazy. So hopefully you're seeing the application of the integration and derivatives and all the other rules, the 5 different things we can do to a series. All right. I'm getting tired. Is this the last one? Okay, this is the last example. So Hopefully you're hanging in here. Hopefully you're not too tired. But here's a secret for this one. This can be rewritten by the properties of logs as this. So now we can find the individual series. This, do we have that? Let's look at our arsenal. Oh, we have this. Couldn't I do a composition where I place x with minus x? It becomes 1 plus x? I think so. So maybe I'll do this up here. I'll call this h of x, and I'll call m of x equals opposite of x. This is crazy. H of m of x. So I'm going to place this in for the x's. Yeah, for the x. And I'm not going to do all these. I'm just going to do my summation form just to make this go by faster. That will be ln absolute 1 plus x, because I replace that with a minus x, which will get me which would be negative 1 k plus, negative x, sorry. Yeah, x is being replaced with minus x. Minus x to the k plus 1 over k plus 1. I'll go ahead and put the minus x here, here, here. So what we get is the first one's going to be positive x, the next one's going to stay negative, the third one's going to become positive. So now we have the series here for ln of 1 plus x. We have the series for ln of 1 minus x here. So we are going to combine the two, because we have the rule, if we have two functions, to get the power series for that, we just combine the power series for each. So we just learned this is x minus x squared over 2 plus x cubed over 3 minus dot dot dot. And this one we already did. It's minus x squared over 2 minus x cubed over 3 minus dot dot dot. Well, then we distribute this minus. We get x minus x squared over 2 plus x cubed over 3 minus dot 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 plus x squared over 2 plus x cubed over 3 plus dot dot dot. Now we combine like terms. X and x gets us 2x. Minus x squared and plus x squared cancel. And then plus x cubed over 3 plus x cubed over 3 is plus 2x cubed over 3. And the pattern follows. The x to the fourths are going to cancel, and then we're going to get 2x to the fifth over 5, and it's going to go on, and that's going to be our series, and that's how you do these. I am so tired. I need to stop. I made too many mistakes. Bye-bye.